Greetings of the day, dear students. In this video, we are going to discuss about the OCC of DC generator, open circuit characteristics for or magnetic characteristics of DC generator, and also we will see what are the different graphs, different names and terminology, right? What are the different variables we are having, and how to find out the critical speed, critical resistance, and also we will do one example on this topic so that you will clearly understand the important points, how to find out the critical field resistance, critical speed. All those things will be covered in this video, right? Yeah. Observe, dear students, this is an important topic and little bit difficult, where most of the students will feel it difficult to understand, right? Now, with respect to the DC generator characteristics, we are having open circuit characteristics, internal or total characteristics, and external characteristics. How do you understand that? If the graph is plotted with respect to the E naught versus IF, it speaks about the open circuit characteristics. Here, E naught indicates the no load generated EMF in the armature. IF indicates the field current. If it is internal or total characteristics, if the graph is plotted between EG versus IA, EG is the generated EMF, right? IA is the armature current. Now, if the graph is plotted between V versus I, V is the terminal voltage and I is the terminal current, right? It speaks about the external characteristics. But for your syllabus, we are having only OCC, open circuit characteristics, or the another name is magnetic characteristics, or no load saturation characteristics. These three names are okay, right? Now, if we observe the OCC, it shows the relationship between E naught and IF at fixed speed. Indirectly, it is just the magnetization curve for the material. How do you understand that? How do you understand its meaning? Observe, for example, if it is a separately excited, we are having a field winding here, Z, Z, right? And you are having the armature winding, A, A. Now, with respect to the field, you have connected a rheostat, and using this variable rheostat, the amount of current that flows to the field winding, IF, can be varied. IF can be varied. Now, depending upon the excitation, at different levels of excitation, different levels of voltage will be induced in the generator. Now, if you plot the graph for different values of field current, for example, if the machine rated field current, if it can withstand up to 2 amps, IF equals to 2 amps, if it's its rated value, at different values, I'll let it be at some point 1, point 2, or point 2, point 4, point 6, point 8 at 1 amp, and at 1.2, 1.4, 1.6, like this up to 2 amps. At different values of current, for example, if this is at some point 6 amps, different amounts of voltage will be induced. If you join all those voltages for different values of field current, you will get a graph shape like this. This is nothing but our OCC. This is nothing but our OCC, open circuit characteristics. Clear? I repeat again. For different values of field current, by slowly varying the rheostat, you will control the current flowing to the field winding. If its rated current is, for example, 2 amps, you will reach 2 amps in steps. For example, in steps of point 0.2, point 0.2, point 0.2, slowly you will reach the its rated value, right? At different values of current, you will observe with the help of this voltmeter how much amount of voltage is induced in the generator, or induced in the generator. That values you will note down. Now we will plot the graph for IF versus E naught. Then if you join that shape, you will get a curve like this. If you observe, this seems to be linear up to certain point. This there seems to be linearly it is increasing. but after reaching certain point, right, now that linearity will not be obeyed. Slowly it takes a curved shape like this, curved in nature like this. Now no longer it is seems to be linear, right? Now one more interesting point, even though the field current is zero, at that time you are having some small amount of voltage induced in the generator. Even though there is no field current, this OA is due to the residual flux, residual magnetism, this OA value. Actually, what should be the case? When there is a field current, excitation, then voltage must be induced, right? But still, at starting stage, even though there is no field current, some voltage will be induced OA. OA amount of voltage will be existing under no load condition, right? So that thing you can observe while plotting the graph, right? Now, uh, if you the this is about the OCC, and observe here IF is 0, still some voltage is induced, that is due to the residual flux. Initial part seems to be a straight line, later it seems to be a curved in nature, right? With increase in the flux density, no longer that straight line appears. Now, on this graph, if you draw a tangent, if the tangent is drawn to the OCC initial part, now the slope of that line, for example, the slope tan theta opposite side by adjacent side, tan theta equals to opposite side by adjacent side, opposite parameter. Opposite parameter indicates what? Opposite axis is what? Opposite is voltage divided by current. Adjacent side means current, voltage by current value, some voltage by current value. It indicates the resistance. It indicates the resistance, critical resistance for that particular speed. That is important. Slope of the tangent to the curve indicates what? Critical resistance for particular speed. If the speed changes, if the speed is changed, again if you have plotted the OCC, right, then you may get some other tangent also can be drawn. Now the tangent drawn to the OCC and the slope of the line gives the critical resistance. That is important. Now observe, dear students, here this is the graph you got, OA curve you got. Now just simply draw a line. OA is drawn to the OCC curve such that a OA line, OA is drawn onto the OCC, right? It is cutting the OCC curve at some point P, LP by PF, voltage by current value, right? Now uh, the slope equals the field winding resistance. The slope of this line OA, the slope of the OA line equals to the field resistance. How do you understand that? At every point on the curve, voltage by current will give you the resistance value R. For example, if critical field resistance is around some field resistance is, for example, around 110 ohms, R. Critical field resistance is RC is 110 ohms. So indirectly, what does it mean? Some tan theta is equals to the 110. Now indirectly, you can calculate the theta. Theta equals to tan inverse of 110. So the line will be at an angle. For example, tan inverse of 110, let me observe, shift tan inverse of 110, it will be around 89.47 degrees, 89.47 degrees, something like that, right? So the value of resistance represented by the tangent will represent the critical resistance, but whereas this OA line represents the field resistance, field winding resistance. But whereas the tangent, once you draw a tangent, now the slope of the tangent represents which resistance? Critical resistance for given speed. That critical resistance is represented with letter RC. With letter RC. Now what about critical speed? One more important parameter comes into the picture, that is the critical speed. Critical speed. It represents nothing but the speed for which the shunt field resistance RSH represents the critical resistance. RSH should represent what? Critical resistance. That means that line should become the tangent to the curve. Then that speed is called the critical speed NC. For particular speed, the field resistance line observe at some speed N, RSH represents the field resistance line. Now for some other at some particular speed curve, for particular speed value, this line will behave like a tangent to the other curve. Previously, this line is not a tangent to the curve at speed N, but whereas the same line became tangent to some other OCC curve for different value of speed. For that speed represents the critical speed. That speed represents the critical speed. Or BC by AC, the ratio of this BC, B, right, C. This became the tangent. BC by AC represents the is equals to the NC by full speed. Now NC is the critical speed. So NC will be equal to how much? BC by AC into full speed. BC by AC into full speed. That represents the critical speed. Clear? Now this line cuts this tangent at some point A. Like this, critical speed and critical resistance are obtained. OCC or open circuit characteristics. Now let me do a small problem on this topic, dear students, so that you will understand it in a better manner. The OCC of DC shunt generator, open circuit characteristics of DC shunt generator running at 1000 RPM is as follows. Estimate the voltage to which the machine will build up if the speed is 100 RPM and field circuit resistance is 30 ohm. Field circuit resistance is 30 ohm. OCC at different values of field current. This is the voltage induced in the generator. At different values of field current IF 1 ampere, 2 amps, 3, so on up to 8 amps he has gone. At different stages, this is the voltage induced. Slowly, first thing you have to do is for different field currents, plot the OCC curve at 1 ampere, 52.5 volts, at 1 ampere, 52.5, at 2 amperes, 107.5. So just first indicates the at different values of field currents, what are the values of the voltages. Slowly join all those points. On joining all those points, we will get the curve OA. You will get the curve OA. Up to here clear? Field current versus this voltage, OCC voltage, E naught. This is E naught. You will get a curve OCC. Now that is plotted. He has specified the to draw RSH equals to 30 ohms line. What we have to do is to indicate the line which indicates the field resistance. The slope of that line should indicate the field resistance. RSH equals to 30 ohms. What we have to do is that voltage value multiplied with any current you take. For example, any field current, 5 amps we have taken randomly, multiplied with resistance. From the basics we know V equal to IR. V equal to IR. You have taken shunt field resistance RSH. You have taken some other field current IF at some random value, but RSH is fixed. If you multiply, we are getting 150 volt. Now on x-axis 5, on y-axis 150, indicate a point. I repeat again, to draw the line onto the OCC, which indicates the shunt field resistance, you just simply multiply the resistance value with current, you will get the voltage, and that value is 5, 150. Now this B point. Now project this line onto the OCC. Join this point through this point OB. Extend this point. It will cut it will cut the first curve OCC at some point A. Now extend this point A onto the voltage axis. Extend this point onto the voltage axis. Now that voltage, now that voltage OM, this OM, OM is around 310 volts is the voltage to which the machine will build up at 1000 rpm. Very, very important. That is the voltage to which the machine will build up at 1000 rpm. That much maximum voltage only it can generate. That is the meaning. Beyond that we cannot get. I repeat again, simply draw the OCC. For the given resistance, multiply it with any field current. Any choice you can take. You can take 3 amps, multiply it with 30, 3 into 30, 90. You just simply join 3 comma 90. You will get 1 point. And you extend that point onto the OCC curve. Definitely it will cut the OCC curve at some point. The point at which it cuts the OCC, extend it onto the voltage axis. That is the maximum voltage it can build up at that particular speed. This is the first part, right? Now, if you draw the tangent, if you draw the tangent to this curve, it represents which resistance? Critical resistance. If the tangent is drawn onto the OCC, it represents the critical resistance, right? Yeah. Now, new curve is to be drawn. New OCC curve at 800 rpm. How the OCC will look like? This is the OCC curve at 1000 rpm. Now at 800 rpm, this is the new OCC curve at 800 rpm. Now this is the new curve. How we will get this? From the old values only we should get this new curve. From the old curve we should get this new curve. New OCC at 800 rpm. How we will get that? Observe. E new voltages values, field current will be same. New value divided by old value equals to new speed by old speed. Now our E new voltage values will be old voltage value into new speed by old speed. Now what is E old? For that particular, if you take any particular voltage value from the OCC data given, for example, for 52.5, what will be the new voltage value? You can calculate for 52.5. It is around zero point 0.8 times old values. Our new value will be simply 0 0.8 times old value. Now, using those new voltages, draw the OCC. Now it cuts the resistance line at C. Now the resistance lines cuts the new OCC at C. Observe. Already this line is existing previously. This line cuts the new OCC curve at C. Now extend this onto the voltage axis. Very simple. Don't get confused. Now this is the point where the maximum voltage can be built up if the speed is at 800 rpm. Previously, how much voltage it is able to induce or generate at the generator? 310 volts. Now the speed reduced to 800 rpm. Because of that, what happens? This is the maximum voltage the generator can generate. How much it is? 230 volts. 230 volts. Right? Now, 230 volts is the maximum voltage to which the machine will build up at 800 rpm. Now, if you draw a tangent to the OCC at rpm, okay, any line EF is drawn perpendicular to the base and it cuts the line OA and OT at B and E respectively. That is what you have done. It cuts the line OA and OT. A tangent is drawn. OA and OT. Now this ratio. Now the critical speed is obtained by NC by N equals to BF by EF. So NC equals to N into BF by EF. Already N we already know 1000 into BF length. The help of BF EF length. BF by EF length we want. BF from here to here, B to F and E to F. This length is required. BF and EF. BF by EF length, right? BF by EF length is 150 by 260 is nothing but 576.9 rpm. So the critical speed is 576.9 rpm. Now the slope of the tangent OT represents the critical resistance. What is the slope? 260 by 5. Opposite side by adjacent side. 260 by 5. The slope of the tangent OT. Observe here. You take any point. This tangent drawn is no this point. Opposite side by adjacent side. The slope of the tangent. Opposite side by adjacent side. 260 by 5 equals to 52 ohms is the critical resistance. 260 by 5 is the critical resistance. Clear? It is simple. So this is what all about the OCC open circuit characteristics of the DC shunt generator. Sorry, OCC characteristics of DC generator. Right? Thank you.